Imagine, imagine your company's network is just entirely compromised right now. Like the hackers are already in.
Right, they have total administrative control.
Yeah, they're inside your servers. They're casually navigating through your operational databases. So do you panic?
Most people definitely would.
Right. But what if I told you that you don't actually have to do anything? Because um, you've engineered the literal physics of your business so that those hackers are entirely powerless.
It's a crazy thought, but it's real.
It is. And we are dismantling a massive assumption today. I mean, for decades, the entire cybersecurity industry has basically been built on this one premise that we just need to build, taller digital walls to keep the bad guys out.
Yeah, but the problem with building a 50-foot wall is that a highly motivated, state-sponsored adversary is just going to engineer a 51-foot ladder.
Exactly.
It just creates this endless, exhausting arms race. And the alternative, which we're looking at in the source material today, well, it completely abandons that fortress mentality.
And that is exactly our mission for this deep dive.
Yeah.
So on the desk today, we have this huge stack of highly advanced playbooks and architectural blueprints. They're focused on critical cyber infrastructure protection, or CCIP.
Yeah, and it's a radical paradigm shift.
It really is. We are going to explore this methodology that just assumes the absolute worst. It assumes a well-resourced adversary will eventually breach your cloud, they will breach your network, and they will get inside.
Because they will. That's just the reality now.
Right. So the goal isn't to prevent the hack entirely. The goal is to engineer your systems so that even when the adversary gets total control, they physically cannot cause catastrophic harm.
Which is such a liberating concept when you really dig into it.
Totally.
Yeah.
And for you listening, we're going to explore how to build these unhackable core operations using a very specific tech stack today. We're looking at Obsidian for knowledge mapping, Google Cloud Platform or GCP for the infrastructure, Cloudflare for edge security, and Google Workspace for executive communication.
So to really understand the mechanics of why this is so revolutionary, we kind of have to start by looking at the ultimate worst-case scenario.
Okay, lay it out for us.
The methodology detailed in these blueprints, it's called consequence-driven cyber-informed engineering, or CCE. It was actually pioneered by the Idaho National Laboratory.
Oh, wow. Okay.
Yeah, and the core philosophy here fundamentally changes what you are delivering to a business. You are no longer just selling security, you are selling absolute resilience.
Absolute resilience. I mean, that sounds amazing on paper, but if you are listening to this and you manage a massive corporate network, you're probably wondering, how does that actually work when the hackers are already inside the house?
Right. It seems counterintuitive, but it starts by identifying what the CCE methodology calls your crown jewels.
Crown jewels.
Yeah. But finding those crown jewels, it completely changes your priorities. You don't start by looking at your routers or your servers or even your customer databases.
Wait, really? You don't look at the data first?
No, you actually start by looking at physics and business logic. You ask yourself, what is the absolute worst, most unacceptable event that could possibly happen?
Give me an example of that.
Well, if you're managing an oil pipeline, the crown jewel consequence you want to avoid isn't a data leak. It's a GCP-hosted controller sending an overpressurization command.
Oh, man.
Yeah, a command that physically bursts that pipeline and causes a massive environmental disaster.
So you basically isolate the single event that causes real-world physical destruction or just completely destroys the business.
Exactly. And once you identify that unacceptable event, you build what the CCE calls kill chain cartography.
Kill chain cartography. That sounds intense.
It is. You map the exact route the adversary would have to take to make that specific physical disaster happen. You document every single stepping stone.
So you're tracing their steps.
Right. You map out how they, say, bypass a Cloudflare web application firewall rule, how they compromise a GCP identity, how they pivot through a virtual private network connection, all the way down to the physical gateway controlling that specific pressure valve.
Okay, so mechanically, it's kind of like designing a highly advanced bank vault.
Yeah, that's a great way to look at it.
Let's say the vault has this state-of-the-art digital keypad. In the old days of cybersecurity, if a hacker bypassed the keypad, the software just told the doors to open, and they took the money.
Right, because the software was the ultimate authority.
But under this CCE methodology, you engineer the vault so that if the digital keypad is compromised or, if it starts sending erratic rapid-fire commands, the vault doors physically, mechanically fuse shut.
Yes. You take the ultimate authority away from the digital layer entirely.
You just cut it off.
That mechanical override is the genius of the whole system. The digital layer is treated as inherently untrustworthy in a crisis.
And looking at these blueprints, there's this fascinating mitigation strategy here that really caught my eye, mostly because it completely abandons software altogether.
The analog fallback.
Yes, the analog out.
Yeah.
It's wild. You spend months mapping out this incredibly complex, high-tech kill chain in your Obsidian software. You track the GCP telemetry, and the ultimate solution you engineer is a workflow where, if the cloud is compromised, the system just defaults to a physical mechanical relay.
Right. An operator literally walks over to the machine and manually overrides the system.
Just a person pulling a lever.
Exactly. And to prepare for that exact moment, the engineering team drafts a break glass standard operating procedure.
And this is where the tech stack comes back in, right?
Yes. They map the complex technical relationships in Obsidian, they publish the simplified procedure as a Google Doc, and then, and this is the best part, they print it out on a physical piece of paper.
A piece of paper.
A literal piece of paper. When the digital dashboards are completely owned by the adversary and flashing red, the human operators have a binder telling them exactly how to run the plant manually.
Honestly, if you sit on a corporate board, this is the exact moment where your ears should just perk right up.
Oh, absolutely. It is a massive relief to executive leadership.
I bet.
In what the sources call a marketing 5.0 context, CEOs and boards of directors are just completely exhausted by the cybersecurity arms race.
Yeah, they're tired of pouring millions of dollars into software that eventually gets bypassed anyway.
Exactly. And this methodology gives them an off-ramp. A chief information security officer can finally look the CEO in the eye and say, look, I cannot guarantee the cloud won't be hacked.
Which is honest.
Right. But I can guarantee that if they do hack us, the business survives because we've removed the digital dependency from our most critical physical functions.
So the adversary might be, like, taunting you on the screens, but the pipeline doesn't burst because Janet in operations just pulled a heavy metal lever based on a paper binder she keeps on her desk.
Janet saves the day.
Janet always saves the day. But okay, to make that work, to protect that physical machinery in the first place, we have to transition from the manual overrides and look a bit closer at the machines themselves.
We have to dive into the world of operational technology, or OT.
Right, OT. This is the domain of real-world physics. We're talking water pumps, power grids, manufacturing lines. And integrating this physical equipment with modern IT cloud architecture creates this massive culture clash.
Oh, it's huge. The IT-OT convergence is where most traditional security strategies just completely fall apart.
Why is that?
Well, the plant managers on the OT side have one religion, and that's uptime. The plant must run continuously, sometimes for decades, without stopping.
And the IT side?
The IT side, managing the corporate cloud, has a completely different religion. They care about security and constant software patching.
So those two philosophies are just constantly at war.
Constantly. And the core issue is that the legacy industrial protocols running these physical machines protocols with names like Modbus TCP or DNT3, they were designed decades ago.
Right, before the internet was really a thing.
Exactly. They have zero inherent security. They don't require authentication or passwords. They were built for a time when things were physically wired together in a locked room.
So they just assume that any command they receive over the wire is totally legitimate.
Yep, they just blindly obey.
Wait, hold on. Why are these industrial machines so incredibly fragile in the first place? Like, if my laptop gets a virus or needs a security check, IT just runs a background scan and fixes it while I'm working.
Right.
Why can't the IT team just run a standard security scan on a water pump controller or, a manufacturing programmable logic controller, a PLC, to see if it's safe?
That is the exact mistake many eager IT teams make when they first try to secure a manufacturing floor.
Really? What happens?
You cannot run an active scam on these legacy PLCs because a simple network scan will literally crash the machine.
Wait, just a scan crashes it?
Yes. These industrial controllers are built with tiny, hyper-focused processors. They're designed to do exactly one thing, like monitor a valve pressure millions of times a second without fail. Their memory buffers are minuscule.
So if you send them standard IT traffic, they just give up?
Pretty much. If you suddenly send them a burst of unexpected IT network traffic, like a vulnerability ping asking, hey, who are you and what software version are you running? The controller doesn't know how to process that request.
Oh, man.
Its memory buffer overflows, it panics, and it shuts down. So by trying to actively check the locks, the IT team accidentally becomes the attacker and causes the exact operational outage they were trying to prevent.
That is wild. So how do you actually bridge this divide without breaking everything?
Well, the architecture uses something called the Purdue Enterprise Reference Architecture.
Yeah, the Purdue model.
Right, the Purdue model. It is a framework for building strict, impenetrable boundaries between different levels of the business. You use GCP virtual private clouds or VPCs and Cloudflare Magic Wand to enforce these zones.
Ah, so you are effectively air gapping the manufacturing floor from the corporate IT network.
Exactly. Making sure standard IT traffic can never accidentally hit those fragile PLCs, even though both sides are technically connected to the broader cloud environment.
Okay, but setting up that boundary solves the accidental crashes, sure, but it creates a massive blind spot, doesn't it?
It does.
Like, how do you watch for actual hackers if you can't touch or scan the physical machines?
You have to use deep packet forensic analysis. Specifically, you utilize GCP packet mirroring.
Okay, how does that work?
Instead of actively pinging the fragile machines, you set up a mirror at the network switch that makes a passive copy of all the network traffic as it flows by.
Oh, so you become a ghost on the network.
Exactly. You just sit there and listen to the mirrored copy. If you see a rogue stop PLC command hidden in that legacy Modbus traffic, you capture it and analyze it without the PLC ever knowing you were there.
That's brilliant.
And then you log those forensic findings into your Obsidian knowledge base, mapping out exactly what the attacker tried to do.
And then you tell the humans what happened.
Right. You push a sanitized, plain English report to Google Workspace so the board of directors knows what happened, all without ever touching the fragile plant floor.
So you are silently guarding the physics. Okay, so we've successfully air-gapped the fragile physical machines, and we have our paper manuals ready.
Yeah.
But that still leaves a massive blind spot in my mind. What happens if the physical plant is safe, but the cloud infrastructure hosting your entire defense network literally melts down?
Ah, right.
Like, how do you survive that? And I think that brings us to moving from physical resilience to autonomic cloud resilience. There is a great term for this in the sources.
Left of boom.
Yes, left of bin. I love that phrase.
It's a concept borrowed directly from military and intelligence circles. The boom is the disaster. It's the massive cyber attack, the regional power outage, the severed fiber optic cable that takes down your data center. Everything to the right of the boom is chaos, damage control, and panic.
And everything to the left of the boom is your preparation.
Exactly, your engineered survival mechanisms. The idea is that you can't always stop the boom from happening, but you can engineer your GCP and Cloudflare infrastructure to absorb the shock and recover instantly.
So we are talking about building an automated self-healing lab. At the foundational level, you use GCP cloud storage to keep immutable, unchangeable backups of your Obsidian vault.
Crucial step.
Which means even if a hacker gets administrative access, they physically cannot delete your core documentation.
Right.
And you use Cloudflare's always-online caching so that if your primary GCP server literally catches fire, the public still sees a cached version of your front-facing assets.
That's the baseline, yeah. But the expert level of this left-of-boom preparation is what the blueprints call chaos engineering.
Chaos engineering. That sounds like an oxymoron.
It kind of is. This is where we elevate the architecture from just being secure to being actively resilient. In a chaos engineering scenario, you design the system to heal itself by removing the human bottleneck entirely. Well, you use GCP's managed instance groups with auto-healing capabilities. The logic is simple, but really powerful. If a server node fails to respond to a health check within a few seconds, GCP doesn't page an engineer.
It doesn't wake anyone up.
No, it ruthlessly kills the unresponsive node and spins up an identical new one instantly.
But let's scale that up. What if an entire cloud region goes down? Let's say a hurricane takes out the whole eastern seaboard of cloud hosting.
Okay, big boom.
Yeah, the health check fails, but there's literally no server capacity in that region to spin up a new node. What then?
If the regional boom happens, Cloudflare's global network instantly detects the massive outage and reroutes your user traffic to other parts of the world.
Wow.
Simultaneously, GCP uses an infrastructure as code tool called Terraform. Now, Terraform holds the blueprints for your entire network. When the region dies, Terraform scripts automatically execute API calls to spin up a completely new, identical infrastructure in a tertiary region.
Like completely rebuilds it in Europe or Asia.
Automatically, from scratch.
And here is the part that really highlights the integration of this whole tech stack we've been talking about.
Oh, the reporting.
Yeah. Once Terraform finishes rebuilding the cloud region, A webhook, which is basically just an automated digital tap on the shoulder, triggers a Google Apps script.
It's so
It
cool.
is. That script automatically pulls the incident logs and drafts a post-incident report in Google Workspace.
Yep.
The system detects its own failure, reroutes global traffic, rebuilds an entire cloud region from scratch, and then literally types up its own paperwork in Google Docs to tell the human IT team exactly what it did.
It handles the entire crisis lifecycle in minutes.
See, that sounds like magic.
Ah,
But I look at that and I have to wonder about the risk. Doesn't removing the human bottleneck entirely make the IT team dangerously complacent?
it's a fair question.
Like, what if the automated reflex makes the wrong call? What if Terraform accidentally rebuilds the infrastructure in a compromised zone? Or what if the health check was just a false alarm? Why wouldn't you want a human to verify the regional outage before shifting the entire global network?
It is a crucial point, and it really comes down to the psychology of a crisis. Why do we automate the reflex? Because in a disaster, human panic is your greatest enemy.
Right.
When the red lights are flashing and millions of dollars are vaporizing by the minute, humans make mistakes. They freeze. They forget the protocol.
They panic.
Exactly. In fact, documentation is usually the first casualty of any crisis. Nobody stops to write down what they are doing when the building is literally on fire.
Yeah, everyone just goes into pure reactive mode trying to stop the bleeding.
Right. So by automating the reflexes, this left-of-boom resilience engine isn't making humans obsolete. It is actually buying them the one thing they need most: time.
Time to think.
It gives them perfect situational awareness and zero panic operations. The automation handles the immediate survival reflexes, allowing the human engineers to step back, read that auto-generated report, and focus on the strategic root cause of the outage. The executives don't have to wake up at 3 a.m. because the system handled the regional outage and logged the report. As the sources put it, this architecture literally sells sleep to leadership.
It sells sleep. You are engineering the panic out of the equation entirely.
Exactly.
Okay, so we've made our own internal digital house unhackable. We've air-gapped the fragile physical machines. We've made our cloud infrastructure self-healing and self-documenting.
It's a solid setup.
It is. But that forces us to look outside our own perimeter. What if the whole neighborhood burns down?
The supply chain.
Right. You can have the most perfect self-healing internal network in the world, but if your regional power grid collapses or your primary internet service provider goes bankrupt overnight, your perfect internal network still goes dark.
And dealing with that external vulnerability is what the blueprints call the P3 layer.
The P3 layer.
Yes, public-private partnerships and ecosystem intelligence. It is the realization that no organization is an island. Your internal security is fundamentally reliant on the security of the vendors, utilities, and cloud hosts around you.
Right. And to handle this massive external risk, the architecture uses something called an automated threat exchange.
Mechanically, this is fascinating.
It is. You configure your GCP cloud to constantly ingest massive streams of external intelligence. We're talking about things like SDIX and TaxDI threat feeds.
Right.
And if you listening aren't familiar with those, think of SDIX and TaxDI as a standardized machine-to-machine digital language that the global cybersecurity community uses to whisper to each other about new threats in real time.
It's like a global neighborhood watch.
Exactly.
Okay.
It tells your system exactly what a new attack looks like before it even reaches your perimeter. You combine that with automated alerts from the Cybersecurity and Infrastructure Security Agency, CISA.
Yep.
GCP ingests all this national-level intelligence and automatically translates it into new Cloudflare Edge block lists. Your perimeter hardens itself based on global intelligence without a human ever having to read a warning email.
But, consuming external threat data is really only half the battle.
Mhm.
You also have to map your physical and digital dependencies. And this is where the Obsidian tool really proves its overall value. See, most risk analysts try to track their supply chain vendors and utility providers in flat Excel spreadsheets.
Ugh, spreadsheets.
Right. And it is practically impossible to see how one failure cascades into another when you're just staring at rows and columns.
Because row 47 says the local water company is fully operational, and row 112 says your backup data center is online. But the spreadsheet doesn't tell you that the backup data center relies on that specific water company for its cooling towers.
That is exactly the problem. So instead of flat spreadsheets, this methodology uses Obsidian's native graph view. You build a visual web of strategic interdependency.
A visual web.
Yeah. You link a specific GCP availability zone to a local utility, to a Tier 3 software vendor, all the way down to your internal crown jewels. You are basically building a massive interconnected map of potential failures.
This sounds exactly like an epidemiologist tracking patient zero, and the spread of a virus on a giant map.
Oh, that's a perfect analogy.
You see all the little red lines connecting the cities and showing how the infection travels. Except here, the patients are third-party vendors, utility companies, and cloud hosts.
Yes.
You are visually watching how an infection or an outage at a small, seemingly insignificant software vendor cascades up the chain to take down your entire enterprise.
And when you visualize it that way, you can see exactly why boards of directors are terrified of blind spots. If you look at the massive global supply chain outages or third-party IT crashes that make international headlines today, they rarely start at the target company.
Right.
They start at a vendor the target company didn't even know they relied on. By using this graph view methodology, you transition from being just an IT defender to being a systemic risk architect. You map the cascading failures before they happen left of boom.
Systemic risk architect. And it completely changes your role in the broader community, too.
How so?
Well, when your Cloudflare Edge detects a brand new, novel attack pattern trying to breach your network, you don't just hoard that data.
Right, you share it.
Yeah, you use a GCP script to strip out all your private corporate information, anonymize the data, and instantly push that indicator of compromise, that IOC back, out through the STIX and TaxDeep feeds to your P3 partners, to industry peers, and to the government.
You become a responsible player in the ecosystem. You spot the virus, you automatically create the digital antibody, and you share it so everyone else's Cloudflare shields go up instantly.
It's beautiful, honestly.
You are actively protecting the ecosystem because a healthy ecosystem is the only way your business survives in the long term.
Absolutely. So what does this all mean when we put all the pieces together? Let's recap this whole journey we've been on.
Let's do it.
We started by tearing down the idea of the 50-foot wall. We look at a highly specific tech stack, Obsidian for mapping the kill chains, and visualizing cascading failures, GCP and Cloudflare for enforcing the Purdue model air gaps and running the self-healing Terraform chaos engines.
Right.
And finally, Google Workspace for translating all this extreme technical complexity into clear executive-level survival plans.
And by combining those tools under the consequence-driven, cyber-informed engineering methodology, we fundamentally flipped the script on traditional cybersecurity.
We really did.
We moved from the exhausting task of trying to keep hackers out to the empowering position of ensuring that even if they are sitting inside your network with full administrative control, their presence simply doesn't matter.
Because they can't break the physics.
They can't break the physics.
Which leaves me with one final, lingering thought for you to mull over as we wrap up today. We've spent this entire deep dive exploring the absolute bleeding edge of cyber engineering.
The bleeding edge.
We talked about machine speed, automated threat sharing via STIX and TACtown feeds, autonomic cloud regions that rebuild themselves from scratch using Terraform, and deep packet forensics passively listening to fragile industrial machinery without touching it.
It is the absolute pinnacle of modern technological complexity.
It is. And yet throughout all of this incredibly advanced engineering, the ultimate unbreakable failsafe, the truest form of absolute resilience that guarantees the company's survival when the boom finally happens, was a physical binder of paper printed from a Google Doc so a human being could manually pull a heavy metal lever.
It is a profound paradox. The more complex the digital web becomes and the more we automate our survival reflexes, the more we must ultimately rely on the tangible, physical world to save us when the digital realm inevitably falls apart.
It really is something to think about. Well, thank you for joining us on this deep dive. As you go about your week, whether you are managing a massive corporate network or just organizing your own digital life, I encourage you to look at the inevitable failures, not with panic, but with an engineer's eye for left-of-boom preparation. Think about the infrastructure you rely on every day. Don't fear the boom. Engineer the fallback. Until next time.